Okay, so today we're talking about something that sounds kind of scary called the coefficient of determination. So on Monday we talked about scatter plots, and then yesterday we talked about residuals, saying, hey, the whole point of a scatter plot and the line of best fit is to make an accurate and reliable prediction for the data. We looked at the residuals and then that correlation coefficient R to say, hey, how close is that line of best fit? How good is it? Today we're kind of on a similar train. So, in our last lesson, we switched on that diagnostic on feature in our calculator, which gave us 2 extra values whenever we did a regression. One value is called the correlation coefficient R, just a lowercase r, which describes the strength of a relationship. So I want to look at an example of some bivariate data and look at how running a linear regression might not work out well for us. So I've done a lot of the math for us here. This first example is the streaming price and the profits. So a large online streaming service has adjusted their monthly prices several times over the years. The monthly subscription fee X and the yearly profit Y in millions are shown in the table below. Like when their monthly fee was $4 a month, their profit that year was $61.2 million. When they bumped their fee up to $425 a month, their year-end profit was $70.2 million. Now for 2 years in a row, they had a monthly fee of $450, but they had 2 different profits, and that's fine. Like that happens. That makes sense because things are going to vary, right? You don't have to have the exact same outcome both years with the same price. So, give me just a second to type these numbers in. You don't need to do that. Again, I'm just typing these numbers in so I can do something on the calculator, but you do not need to worry about typing them in right now. Okay. So, here is a scatter plot of that data. If you run a linear regression, you're going to get the following values. If I go ahead and do that, stat calc fourth option, I get this stuff here. Okay. I'm going to make it draw a scatter plot, and then I'm going to do one extra little thing when I get down here. So now what my calculator just did is it's got, whenever I go to the graph, the scatter plot drawn, and whenever I ran that, whenever I said store regression EQ, and I put Y1, it automatically typed it in for me up here. Again, you do not need to know how to do this. But whenever I go to my scatter plot here, here's what the line of best fit looks like with that data. Does that look like a good line of best fit? Absolutely not, right? I mean, it kind of misses all these, it's a little bit above them. It misses all these, it's a little bit below them. And it misses all these, it's above them again, right? And we can see that it's not a great line of best fit looking at this value right here, R. That's what we talked about yesterday. This value, called the correlation coefficient, should be between -1 and +1. The closer it is to -1 or +1, the better the line is. Well, this being at -0.5 says that this correlation is weak. So this y equals -6.9x plus 113.9 Probably not a good line, and we can see that on the graph. But yesterday the problem that we talked about was, well, maybe there's an outlier. That's not the problem here. The problem isn't that we have an outlier. The problem is how we're trying to model this data. When we run a regression with that diagnostics feature selected, we get the R and R squared values. The one that we didn't use yesterday, R squared, is called that coefficient of determination. And what that number does is it describes the type of the model that we're going to be working with. And depending on what it gives us for R squared, it might tell us, hey, maybe don't use a linear. Maybe use an exponential or quadratic. So that number is always going to range from 0 to 1. So R is from -1 to +1, but R squared is from 0 to 1. The higher that value for whatever type of regression you ran, the more appropriate the type of model. The lower value, the less appropriate. So in the above example, we have an R squared value of 0.2701. Again, looking at this R squared value, 0.270, I rounded it off to 1. That means that a linear model is a really terrible choice. It means it's only 27% accurate. So the other two types of functions we worked with a lot in Math 1 are exponential and quadratic, and we can run a regression for those too. Again, I went ahead and did all the typing and button pushing for you so that we could just talk about the outcomes. To get a quadratic regression, when you go to Stat, Calc, the fifth option quad reg is what you'd be looking for. If you just press the number 5, it'll automatically select it. For an exponential regression, you can scroll down to option 0, or just press the 0 button for EXP reg. So, these are the outcomes you get for both of those regressions. With those diagnostics on, I see for quadratic, R squared. Now y'all, I have no clue why for quadratic, R squared has a capital R. Everything I looked up online was like, yeah, we don't know, just someone decided it was capital letter, but it's the same thing. There's like, it's a difference without a difference. Okay? And then exponential has this R squared. So of those three choices, linear is about 27% accurate. Quadratic is about 98% accurate. Exponential is about 31% accurate. Of those three choices, which one seems like the best option? Definitely a quadratic. Because that's got the highest R squared value, that means we should use a quadratic. So what I'm going to do now is run that quadratic regression and do that little store thing that I did. And now, whenever I go to my graph, that parabola definitely goes through that data. It follows it much more closely than the others. And that's why we have that R squared value being so high. Does that sound okay?
Yes.
Okay. One other thing. Because the quadratic is the highest, the best model is, we've got to be able to look at these numbers and say what the actual quadratic function should be. Now, you got long numbers, we're going to round it off. Negative 9.49, I'm going to round that off to negative 9.5. 113.73, I'm going to round that off to 113.7. Negative 242.3. So the model is y equals negative 9.5 x squared plus 113.7x minus 242.3. That is a lot. All quadratic expressions are going to be something x squared plus something x plus something.
So A and B are always x.
So A is going to have the x squared with it, B is always going to have the x with it, and C is always just going to be a constant without it. Now, with this, we could use it to answer questions like, what's the expected yearly profit if the monthly subscription was $6.50? Or what subscription price would maximize their overall profit? We're going to save that for now. The whole point of this is to be able to figure out what type of function looks best. Any questions so far? Smooth. Okay, on the back, let's look at an example together. Example 2, antibiotics. When a person takes antibiotics, the concentration of the antibiotic in their bloodstream, here it's in micrograms per milliliter of blood, decreases over time as the body filters it out. Below are the results from 2 different trials with the same patient of the antibiotic levels in their bloodstream over a period of 10 days. So we've got 2 different trials, and we do see that things went differently the first time than the second time. Like after 1 day on the first trial, they were down to 500. Here they were down to 550. So this still had more antibiotic in the bloodstream, and that's just going to be natural variation. That happens. Do what?
That's good.
I wouldn't say it's necessarily good or bad, it's just different, right? And these follow different trajectory. I would say something like, something about this pill made it dissolve faster than this pill, or maybe during the second trial this person was drinking less water and so their body wasn't flushing out the stuff as quickly. I don't know. I'm not a scientist. But what I do have is a scatter plot of all these points. Now, you can see this scatter plot is kind of like massively scaled on the y-axis because it had to go all the way up to 1,000 and all the way down to basically 0. But on the x-axis, I just went from 0 to 10 because it's just over a period of 10 days. So what I would like for you to do, grab your calculator. If you don't have one, just grab one from an empty desk, please. We're going to run all 3 types of regression. At first, all of this is just going to feel like pushing buttons just to push buttons and write stuff down. We're not doing any math here. We're just copying down some values so that we can compare here in a minute. So first, let's reset our calculator. Second plus 712. Now, in doing that, we did turn our diagnostics back off. So yesterday, what we did to turn our diagnostics on, if you'll press second and then 0 to go to the catalog, again, second, 0 to go to that catalog, and then scroll all the way down until you get to the D's. Find diagnostic on, hit enter, and enter again. It'll just say done. That is us just flipping a switch on our calculator saying, hey, when we run a regression, tell us how well that model fits. Again, to catch us all up, I pressed second, and then the button 0 to go to the catalog. I scrolled all the way down to the D's. Found diagnostic on, hit enter, and enter again, and it'll say done. Now, I'm going to go to Stat, Edit. In the first column, in that L1 column, I'm going to have to type in 0 through 10 and 0 through 10. So type in 0 through 10 twice, because we're going to combine all of this data into one. Then in L2, type the 1,000 down to 1 and 1,000 down to 2. So that's 22 numbers we're typing in both columns. we're going to run all three different types of regression and just write the stuff that it tells us down. We're not doing any math here. We're just writing stuff that our calculator tells us down. So stat, go over to calc. For the linear, select the fourth option, lin reg, ax plus b. I also just realized there's a typo on this paper. This should say y equals ax plus b, not ax squared plus bx plus c. I just copied and pasted this box over, but I forgot to change that. So, when it gets to this screen, it gives us a is about negative 74.1. B is 559.3. R squared is 0.617. Remember, for R and R squared, we're going to round to the nearest 3 digits. And then R is negative 0.785. Let's run the quadratic regression. Stat, calc, fifth option. Again, I'm just going to round these off to the nearest 10th. For the first three, we get A is 18.4. B is negative 258.5, bless you. And C is 835.9. And then R squared is 0.914. Do what? Can you hang out a little bit longer? The exponential regression, stat, calc, you can scroll down to option 0 or just press the number 0. It gives me A is about 987.7. And B is 0.5. R squared is 0.988. And R is negative 0.994. Okay, so what do we do with all these numbers? Looking at the R squared values for linear, 0.617 basically means that this is about 61% accurate for a linear model. For quadratic, 0.914, approximately 91% accurate if modeled by quadratic. For exponential, 0.988, approximately 98.8% accurate. Of those three, the most accurate model is an exponential. So we're going to go with exponential. Now, y'all, a really hard part of this is being able to write down what the actual equation is. Okay? Exponentials, it gives you this template, y equals, go ahead and write that down, A times B with a little up arrow looking thing, x. I don't know why your calculator doesn't put the x as a little exponent, because it's totally capable of doing that. But how this should really be written is y equals 987.7 parentheses 0.5 to the x power. 987 times 0.5 to the x power. We could use that to answer questions like how much antibiotic is in the bloodstream at like 1.5 days by plugging in 1.5 for the X1. We're not going to worry about that for now. What I do need you to do is grab a computer because I want to talk about how Desmos can make this a lot easier. So if you would please grab a computer and go to Desmos. The link desmos.com/calculator is up here on the board. It's also linked at the top of your canvas. So with Desmos pulled up, what we're going to do is click the plus sign in the upper left corner up here and select that third option down, Table. That's going to give us a table that's kind of similar to our L1, L2 in our calculator. And then let me give you a new sheet of paper so that we can work with a little bit more data. So on this new sheet, I've got a set of data for number 1. It shows the number of bacteria in a cell culture after X hours. We're going to type these X's, all of them, the 7 through 32 and the 56 through 98 in X1. And then I know they're big numbers. Just carefully type them in. You do not need the commas. Type in the 200 through 17,487 million in Y1. So carefully take a few minutes and type all of these X's in to X1, all of these Y's in to Y1. Okay. So at the bottom of your notes, it has the rest of the instructions here. So we've typed our data into X1 and Y1. Number 3 says select the type of model you want to use or use all 3 to compare. You have to type in a formula for the general form of each function. So this is the part where Desmos makes it seem like, wait, how is this easier? It honestly is a little bit easier than your calculator. In the next line down, not in this table, but in the next actual row that you can type in, we need to type in this linear model, y1 squiggly mx1 plus b. To type that in first, the letter y. We're going to be typing this in. In fact, we're going to type all 3 in by the end of this. So type in the letter Y. To type in the little 1 that's like a subscript, just press the number 1. It'll automatically pop down. And it says 10 element list. That's because you've got 10 things that you typed in the Y1 column. The next thing is this squiggly. The squiggly line comes from this button right beside the 1. If you hold down Shift and then press that button, it'll give you the squiggly. What that is asking Desmos to do is say, hey, I need you to fit a function model to the information in Y1, and eventually we're going to say X1 as well. Now usually we say a linear function is y equals mx plus b. That's exactly what we're about to type in, except mx, put a little 1 after it, plus b. Again, to get the little baby 1 after it, just press the number 1 and keep moving on. And you can see it automatically pops up with a bunch of information. The statistics r squared and r are there, and the m and the b are there. Okay, now we're going to jump over to a quadratic. So start out with y1 squiggly, just in the next row down. A quadratic, the general form is ax squared plus bx plus c. That's exactly what we're going to type in. But after we type the x's, we have to put a little 1 after both of them. So ax1. To get the exponent of 2, if you just press that little keypad and select this a squared option right here, it'll automatically put in a little exponent 2 for you. Plus bx1 plus c. That gave us everything that a quadratic regression in our calculator would give us. Last one, y1 squiggly. We're going to type in the general form for an exponential, which is just a parentheses b to the x power. A parentheses b, exponent x1. There's one thing that pops up with the exponential regression that doesn't with the other two. You may see that little log mode with a checkbox. You need to check that. Again, that log mode, you need to check that. It'll slightly change what it's got written down there for you. The TI calculators already have that selected. Log mode is something that you do not need to worry about right now. It's just a setting that needs to be turned on. Okay, that's like a math 3 thing talking about how exponentials get really big really quickly. Okay, so what this is the same as us pressing StatCalc 4, StatCalc 5, and StatCalc 0. Okay? Now that we've got all of that, we can compare all of these models. Now, I don't have the scatter plot on my screen right now, and I'm not too concerned about it. I mean, you could zoom out a bunch, but with most of these scatter plots, it's going to look really bad. You just have to tinker with the window to get it. I'm not worried about that, also because on your practice paper, the scatter plot's already drawn for you. Okay? So, A says identify the type of function. We need to write down the r squared for all 3 of these. I'm just going to round it off to 3 decimal places. So for the linear, r squared was 0.495. For the quadratic, the capital R, which is a difference without a difference, really, the capital R for the quadratic was 0.8198, so about 0.82. And then scrolling down to the exponential, I see after I've got log mode turned on a lowercase r squared of 0.992. Of those 3 options, which has the highest r squared value? Definitely exponential. So that's the choice we're going to go with. B says, okay, what's the equation? Now that you've said exponential is the best choice. So hopping back over to Desmos. I'm going to put these two numbers, this A and B that I've got here, rounded off, into this format, starting with y equals. Don't have to write the y1 squiggly. Here we're just writing down y equals. A, I'm going to round off to 204.7. You don't actually write the squiggly down. You only ever type it into the calculator. So 204.7, parentheses, B we're just going to say is 1.1 to the x power. Do what? Again, you don't need to worry about this, but I'm going to adjust the window of this so that we can see all three. Let's see, the x's go all the way up to 98, so I'm going to take it to like 150. That works. And then the y values go all the way up to 17 million, so I'm going to take it up to like 20 million. So there's my scatter plot and the linear option. Definitely not a good option. And it says that the linear option is only about 49% accurate. Let me hide that and pull up the quadratic. Hey, that kind of does follow the trajectory a little bit better, and it says that the option is about 82% accurate. But we had a more accurate option with the exponential down at the bottom. That follows it almost to a T. That's why it's 99% accurate. Okay, last question that we got to do here. Says, okay, great, you've got the function. How many bacteria will be present after 24 hours? We're going to take that 24 and plug it in for x. You can type that into Desmos, or you can type it into your TI calculator. Either way is totally fine. You will get a decimal value, that's fine, just round it off. That gives me 2016.24. So about 2016. That should make sense because 24 is between the 9 and 28 on this table, which means our answer should be between 1 and 6,000. I'm almost afraid to ask this. Can I get a scale of 1 to 5 on how we're feeling? Okay. Now, if you want to, you can use your TI calculator, but I'm going to really push using Desmos here, because once you've typed in these y1 squigglies, you don't have to type it in again. You can just go back up here, click back into your table, and just start clearing stuff out. Now, the only thing you got to be careful about, a lot of people in my first period, somehow their x1, y1 up here got changed to like x4, y4. It's like they added a new table. If you do that, just go back up here and make sure it says x1, y1. You can actually click into it and change what it says. So to answer questions for number 2, just start typing 0.31, 1.2, 3.1, 3.5 into that table, and this stuff is automatically going to start running the numbers for you. And then because I've zoomed out a bunch on my graph, it's just all over the place. You can just click the home button up here. Take it back to your default zoom. If you want to zoom around, you can, but it's already plotted here on your paper for you. But since I already had those Y1 squigglies typed in, everything's automatically updated down here. Any questions, y'all?